Everyone, my name is Grey Cantoma. I'm from GREYTEST Design Consult. This is my WhatsApp contact. You can reach me on this number, or you can call me on any of these numbers. Okay, today I'm going to be showing you how to design a beam using the RCC spreadsheet. Like I said in the previous episode, this is actually a very great package that I will always want to encourage you, most especially if you are a beginner, to always start with RCC spreadsheet like this, or you can start with the RCD 2000 owned by Victor O. Oyenuga. So in the previous episode we were able to design our slab. So in this episode we are going to be focusing on beam. Now, to design our beam, all we need to do is to go back to our general arrangement. If you miss out on the previous one, you can go down below the description of this video. You'll find a link to that channel. Make sure you visit the channel and keep yourself busy. Okay, all right. So if you look at this now from our general arrangement, based on what was arranged here, this is beam 1, and then this is beam 2. Okay, so on this video we'll most likely talk about beam 1. If time permits, we'll also go into the beam 2, but they are very similar. Okay, so if you see this, this based on the arrangement that was done, this is going to be 230 by 450. If that is correct, all I need to do is to go back to my spreadsheet. Now when I come to the spreadsheet, here, I will specify firstly the number of span, and then the number of span on this design is 3. We have 1, we have 2, and then we have 3. So we have 3 spans. So I am going to type in 3. So 3 is actually what I have here, and then the maximum span that I have in that beam is what I'm going to check for now. We'll go back to the general arrangement and I will check. You will discover that all the spans are actually equal, so I will just pick one of them, which is going to be 3830, and that is basically what I'm going to type in here, 3830. So that will be 3.83. okay, and then the depth of that beam is actually 450, if you can remember, and then the breadth of web is 230 because the width of that beam is 230, and then the height of flange is 150, which is actually the thickness of the slab. If you look at it from the cross section, 150 from that slab is actually going to be 150 from that beam is actually going to be entering the slab. I don't have a beam cross section here, but that's basically what it means. So you will be having 150 part of that beam will be entering the slab, which is this. If you look at this drawing here, you are having this part, you have this other part here, which is this. We have this part here, which is this. Let me just use like a cycle, this other part, and then if you look at this other part here at the top here, this is another part. So this entire part at the top here is actually part of the beam. Is going to be casted with the beam, with the slab, monolithically. Okay, so they are going to be casted with the slab. So this other remaining part that is remaining down is 300. Okay, so that's basically what it means. So I will come back here, and height of flange is 150. Then this BF is the breadth of the flange. This is actually gotten from a very simple straightforward calculation, which I'm going to be showing you the breakdown of that calculation right away. So if you come here, I have a breakdown here. Under here I have the beam load, we have the self weight of the beam, and then we have the breadth of the flange. So in every beam you can either have it as an L beam or as a T beam. Okay, so let's come back to this diagram and check what type of beam is this. Now this is beam 1. If you cycle this part, you realize that it is actually going to give you a shape of a L. So this is basically an L beam. Okay, but in the case of this beam, if you cycle this part and cycle this part along the support here, end support, you realize that this is giving you a T shape. This is also a T shape, which makes this beam a T beam. So but this particular beam is an L beam. So that's basically how to know if a beam is T or L. So because this beam is an L beam, so from here you can see the shape is L beam. So I will leave everything as it is here. I can simply just maybe change the cover of this my particular all the covers. I can do a little change here and change the concrete cover. Then the BF here, all I need to do is to come back and do a simple calculation, which I may probably not have to do that calculation, but I'm going to show you. You can take out your time and just pause this video at this point to understand what was done. Is a very straightforward calculation. This value of 0.07 times maximum span times BW, which is the breadth of web, is actually the value of 0.07 is a constant. That is why I will always encourage you to get this simplified reinforced concrete by Victor Oyenuga. There is one other particular one that is actually specified for students that I used to have. I will encourage you to have it. I'm not sure if you can get it in any of these bookstores, but I was able to get it from someone. Reinforced concrete design, a student / designer's companion, is actually a very good guide. You will see a total breakdown of most of these calculations there. So this is basically how I got the value of 498. So all I need to do is to come back here into this and type in the value of 498. So you can see that red indication has actually gone off by typing the right breadth of flange. So then the self weight of this particular beam can also be gotten from a very simple straightforward calculation as well. If you come here now, if you check for your L beam for 230 by 450, is different for a T beam of 230 by 450. So I'm also going to be showing you that by the time we go to the T beam. So if you look at this now, for the self weight is going to be weight of concrete plus self weight of plaster. Okay, so what is the weight of the concrete? The density of concrete times the factor of safety, which is 1.4. By the time you do all of this, is going to give you a value of 2.23 rather, and then that of plaster in the long run you have a value of 0.69. By the time you sum these two together, you are having the value of 3.01. So all I need to do is to come back here and type in that value of 3.01. So all I will do here now is to type the value of 3.01. Okay, so the dead load, which is in kilonewton per meter, it's a value that you actually get from the slab. Okay, there's what we call the equivalent load that you get from your slab. Okay, so I'll be showing you how to actually get that value. So for our equivalent load on beam, it is very important. This is actually the load that is actually coming from our slab. So that load now is actually what we are going to put in here. Okay, then let's jump right into it. immediately. Now if you come here, I have a breakdown of that calculation which I call the equivalent load on beam. Now the equivalent load for on beam on a two-way slab is different for that of a one-way slab. You can see this is for long span is 1/2 times WLX, which is the short span, everything here in bracket 1 minus 1/3 k raised to the power of 2. So for short span is 1/3 LX, for one-way slab is 1/2 WLX. Okay, so you should note that the k is equals to LX all over LY. So you can take your time to go through this carefully in order for you to have a better understanding of what I'm talking about. So if you look at this here now, is a breakdown of the calculation which I have done. If you check for the long span now, which is 1/2 WLX, this is the formula which we are going to be applying. This 10.52 is the load which we got from the beginning. If you can remember from here, this is the total load coming from the slab, which is 10.52. When you do 0.15, which is the depth of that slab, multiplied by the density of the concrete, you add your finishes plus your partition, everything gives you this, and then we assume a live load of 1.5, and then we do this design and we were able to arrive at this. So this is basically all you need to do to actually get this value of 10.52. so this is the value which we assumed from the beginning, but you know the live load, which is the imposed load, they vary based on the class of building that you are designing for. It comes in different category, whether you are designing for a residential building. Those values are not constant. I will always encourage people to lay their hands on Simplified Reinforced Concrete Design by Victor Oyenuga, or you get the Mosley and Bongi. Very, very important, okay, in order for you to have a deeper insight of what I am actually talking about. All right, so by the time you are done with that calculation, this is what we were able to get along the short span. You know, for that two-way slab, we have the long span, we have the short span, which I was showing you here. This is the panel here, this is another panel here, this is another panel. All of this panel, they have their load that are actually acting on this. There is what we call the triangular load, trapezoidal load, and also the triangular load, trapezoidal load, and yeah, that's basically it. So all of those loadings are the kind of loads that are being acted on this. So if you look at this now, we even have a rectangular load. So if you look at this now, this is basically how this loading is going to look like on this. I have explained this in RCD 2000. I have also explained this vividly even in my even in protastructure. Protastructure will give you as this. So this is basically how this slab loading is going to distribute. So but in a case where you have the panel is a square, where you have a square panel, everywhere is going to be triangle, triangle, triangle. So the whole loadings are going to be triangle. So the load from here is what is acting on this beam. The load here entirely along this trapezium is what is acting here. Along this entire trapezium is what is acting here. This is assumed to be the center. Then this triangle here, the entire load here is going to be acting here. Now if that is correct, what that means is that the load here and the load here are actually going to be the same. The load here and here are actually going to be the same. So this one is acting here, this one is acting here, this one is acting here, this one is acting here. Similarly, what I have here is basically what we are also going to have in this other panel, because they are actually the same. So if you look at this now from here, if you are designing for this beam, definitely this beam is going to be carrying more weight than this beam, because this load will distribute here, this load will distribute here. Okay, so but if you remember, this load is just carrying, this beam is just carrying the load coming from here alone, but this one is carrying, this beam is carrying from here and also carrying from here. This beam here is carrying from here. This is actually very, very interesting. I will encourage you, lay your hands on some of my videos on RCD 2000. You will understand what I'm saying way more better, and I have talked about this using the protastructure as well, so you understand how these loadings are actually being distributed. So the equivalent load that is going to act on this particular beam is the load that is coming from this particular slab, okay, to this point. Then there is another load coming from here now to this point. Okay, so and then at this point also we have a load. Okay, now if you check this now, the load that is going to be acting on this, I'm going to be explaining it as we go further. All right, so so the next thing here we'll do is to, sorry, I'm looking for the things here are choked. All right, so I'm going to be picking that value which I got from here as 13.43 because that is along the short span, and that is what I will be putting there. So so this will now be 13.43, and then you can see this is the information we have. Now the imposed load, like I said, it varies based on the class of building. You have residential, yeah, so if we assume this to be a residential building, the value is 1.5, okay, but it varies. We have value even up to 12 point something, so they change, they varies, it's not a constant. Okay, and then the entire value here now is 25.4. Now this is one area I want to always bring your mind to, very, very important. You can see the operating instructions. It tells you that enter data in blue cells. So the blue cells, these are blue, these are also blue. These are the data you can enter. Okay, only 3 or more spans with UDL, so you can do a 3 or more spans with UDL. Red messages indicate entry errors. So if you have a red message, if you can remember from the beginning when we had one particular value here, it was showing us red, it's telling us that there is an error, so that information is not correct. That is basically what it's telling us. And the BF normally automatically, this software helps us to, this spreadsheet helps us to generate our BF automatically. All you need to do is to pick the value and type it in here, but I was able to explain that anyway while we're on it. Okay, so right now I have successfully done the entire design as far as this particular beam is concerned. Okay, that has actually been done, but if you can remember, what this particular beam is requesting us to use is the maximum span, although we have another span. Okay, all of them are equal actually, so all of them are actually equal. We don't have a difference in their span, so this is also equal with this, and this is also equal with this. So all you need to do is to pick one particular span among them all and actually subject it to that particular load. Okay, so that's basically all you need to do for that particular design. Although in this, let's check something. Let's see. Okay, the load we are getting from here, 13.43, is higher than 9.1, so it is advisable to pick the maximum span, and then you can subject it to the highest load actually, which is 13.43, is higher than this. If not, I would have been able to show you how this one will actually work when it comes to a one-way slab, but I was able to explain anyway that your your highest load, your load, what do call it, your main bars are actually going to spread along this short span, along it. I was able to explain that previously. I was able to explain that, and that is why when you look at a one-way slab, you will see that the indication here when it comes to this is different from this when it comes to a two-way slab. You can see this crosses each other. It's telling you it's coming in two different ways. This one is telling you it's coming in just one way. And what this actually means, all your main bars are going to be spread along this, and then this beam here and then this beam here are literally not carrying any load. That's basically what it means by a one-way slab. So when they say a slab is one way, that means the load from that slab is only spreading along this beam and also along this beam. There is no load that is acting on this and also on this. So that is actually also very similar when it comes to a cantilever. Most times, most of our cantilever are always one way, and in that case the load will actually come back to just that particular beam at this side. Most likely this one is literally not doing anything. So that's basically what one-way slab actually means. So if you love what you are seeing, just like this video and give it a thumbs up. Subscribe to this channel because it's actually 100% free. Click on the bell icon so as for you to always get a notification whenever I post videos. I post videos like this on a weekly, sometimes on a daily, just to encourage as many that actually want to have a deeper insight of design. Okay, then if you look at this now, you see bar cover, single layer, bar spacing, deflection, shear links. Everything is actually valid and everything is okay, although there are some little red indication that is telling us it's probably critical. So if you see the links here, we have the reinforcement is Y10 at 300 spacing. Here at this support is Y10 at 275 spacing. Here is Y10 at 300 spacing. So when you are doing your detailing, you have to take note of all of this information and do the spacing right. So similarly with this, you can see the links is telling us 10 10 10 10. The legs is 2 2. So we have two reinforcements. We have two top, two bottom, and then the spacing here at 200 200 200 for the leg. So that is basically what we have been able to do in the RCC spreadsheet. This is basically how to come about your beam design using the spreadsheet. It's very important to actually always start with this. Is the closest to a manual design that you can achieve compared to most of the automated softwares that will do everything for you in the background without you getting to understand what is going on. So this is the closest, and RCD 2000 is also good. Either you start with this or you start with RCD 2000. I always encourage students that are actually beginners to always start with this or the RCD 2000. So make sure you stay safe or you stay blessed, and stay blessed. Thank you.